Everyone. So today we're going to be talking about resonances, which is one of the first big topics for test three. So with resonance, there are a couple major rules that we need to go over first before we can even get into start like drawing the structures and drawing the different resonance structures in general. So the first rule that we have is only electrons move, never atoms. So with that, if you see a lone pair, you can move that. If you see a double bond, that can be broken and moved around, but you can't move a hydrogen from one atom to another. That breaks one of the fundamental rules of resonance. So one of the next rules is only I electrons. So double bond electrons, things like that, are the things that are being moved. And then lone pairs, like I just said, can also be moved, but never break a sigma bond or a there's a single bond between atoms. That's one of our big um, no-nos with resonance structures in general, as it completely violates the deficiencies we'll get into in just a minute. So our next rule is the total number of electrons remain constant in the original and in the resonance structures. So if you have 10 electrons in the original and you end up with 12 or with 8 in the resonance structure that you drew, you need to make sure to either add them or take them away if you've accidentally put them in there or something like that. And the last one, which I think is super important in general, is that the net charge or the overall charge of the molecule has to remain constant. So if your original molecule has a net charge of zero, and then you have a resonance structure with a negative charge or a positive charge, there's something that has not been done correctly in that resonance structure. So you always need to make sure that if you have a neutral in the beginning, that you have a positive and a negative to cancel out those charges in the next one. So now kind of getting into some of the deficiencies. So we have eight major deficiencies that kind of like break down um, how good or bad a resonance structure is. So starting at the top, going to the bottom. So the top ones aren't super bad um, issues or anything, but as we get down to like seven and eight, those are deficiencies that we do not want in a resonance structure at all. So to start off, we have our third row or greater atom exceeding the octet. So that's like an atom like sulfur. We know that it can have that expanded d orbital. It looks something like that, has some extra atoms or electrons, extra bonds and things like that. That one's not too bad. Okay, if that one happens. And then our next one is isolated opposite atom charges, but remote. So that's kind of showing or saying that we have a structure, say it was something like this. So when we say remote, that means there's an atom in between the two um, atoms that have a charge. So even though the charges look close together in this case, I could draw this positive charge beneath the N. Now they look a little bit further away, but this is just showing that they have an opposite, the negative and positive cancel out to have a neutral charge, which is good. Um, and they also have an atom separating them, which is good as well. So then when looking at sextet atoms, that's a little bit like our carbocations, or it's exactly like our carbocations. So we see just a carbon, just like that, doesn't have its full octet, it's missing one of those bonds. Um, this is something you'll see a lot in rings when we're doing resonance structures or just kind of in general. You'll see a lot of sextet carbons, things like that. So this is a pretty decent one, not too terrible, especially when it's on its own or something like that. So for our next one, we have the positive charge on electronegative atoms. So this is going to be our FO and N, some of those atoms that can do hydrogen bonding. If we see a positive there, this is where we kind of start getting a little, we don't really want to see that just because those atoms want a negative charge, if any charge. They want to be stable, obviously. But if they want to have a charge, it's going to be a negative because it's a very electronegative atom. But when looking at something like that, we can draw a structure. So that gives a positive charge to that oxygen, which is it's not fulfilling its octet, doesn't give it the charge that it wants. So that one's starting to get a little unstable, and it's just going to continue as we get down the list. So now we're looking at isolated opposite atom charges on nearby atoms. So before we had up here for number two, they were remote atoms, but now this time the charges are on nearby atoms. So CH3, C, there's our sextet carbon right there. So now on nearby atoms, that means the atoms are touching each other. They're directly connected and they have opposite charges. So this is where we start to get pretty unstable. And then our next one is the last one that we are even able to have in a resonance structure. So fewer total bonds than another resonance form. So like breaking a bond and just not even having the same number anymore. So when looking at that, a lot of times this might happen with pi bonds. So something like this, we have a pi bond right there in the middle of those carbons. Everybody has a full octet, everything is shared. But then when we have our resonance structure being formed, we end up generating a sextet atom right there. And then we have this carbon anion over here with a negative charge. So we go from six bonds, we'll say, total in that structure. And then on this one over here, we have five bonds, which is not ideal, not very stable. So then number seven, this is one of our really bad ones. Seven does not want to happen at all. Um, so I can show that. And it's kind of like what we call our Texas carbon, or when a carbon has five bonds, kind of looks like a little person or a starfish. Um, but when it exceeds the octet, especially for carbon in this case, super unstable, will not happen. And I'll get a little bit into more about why and like what this means for resonance structures in general. And then our last one is going to be so when sigma bonds are present in another form, are missing or moved. So before I mentioned you cannot break or move sigma bonds. Um, and this is going to reinforce why. So if we have this structure, a little alcohol, a little propanol right here, and then we draw a resonance structure. So we'll end up with negative charge there, a little positive there. We've broken we've broken this sigma bond that's connecting the oxygen and the carbon, which makes this extremely unfavorable and unlikely to happen. So a couple things to kind of reinforce why seven and eight cannot happen and just general rules. So in general, resonance forms with fewer deficiencies are much more stable and contribute more to the hybrid. With that being said, so like obviously if they have fewer deficiencies, it's better, contributes more to the hybrid. If it has more deficiencies, it's going to contribute much less to the hybrid. And then if both of them have two deficiencies or they have the same deficiencies, then they both contribute equally, which is a big part for like the problem set and the test, making sure you can tell which one contributes the most, um, or if all of them do, knowing that. And then one of our last things for our deficiencies. So resonance forms with deficiency seven or eight, they are not going to happen. They are super unstable, um, and not likely to occur. Also, if we have more than three deficiencies, these resonance structures should be omitted or just left out. And with that in mind, so like you can have one, two, or three deficiencies, and technically the resonance structure is a possible option, but forms with two to three deficiencies should be left out if there is a better option. And it just goes back to the stability. So if you have something with the zero deficiencies and you have one that has a positive charge on an electronegative atom, that first one's going to be more stable, going to be more contributing to the hybrid and stuff like that. So making sure that you're paying attention carefully to what's going on with those. So now we're going to talk about some of the classic moves that we like to use in resonance. And this is kind of just talking about like things you're going to see often, making sure you're looking for this in structures that Dr. Bright gives you on the exam and stuff like that. So our first one is going to just be breaking a pi bond. So with that, we're basically just going to see this pi bond. We'll say the electrons are going to go there. So that'll give us structure. We've broken that pi bond in the center. The carbon on the left has lost those shared electrons. It's going to be a carbocation. And then the one on the right is going to gain those electrons right there and get a negative charge. So our charges overall, zero, zero, which is what we want. We want to have neutral charges if the original one is neutral. Everything works out. Now, the one on the right obviously does not contribute as much to the hybrid as our first structure because of um, we have that sextet atom with the carbocation over there. And then we also have, when looking at the two charges, we have isolated opposite charges on nearby atoms. So two deficiencies in that one. Not terrible, but not the greatest either. So next, a very, very, very common one is carbon, oxygen, double bonds. So our carbonyl groups, when you see things like this is very common. Definitely need to be looking for these in our structures. So we're going to break this double bond. Oxygen's okay having a negative charge, so it's going to accept that. And then when we draw our resonance structure, we're going to have C, just our sigma bond there since we broke the pi bond. Our oxygen is going to gain a positive charge, and then our oxygen is going to get three lone pairs and gain our negative charge. The charges cancel out. We still have a zero charge for both of them, which is good. And then we have another sextet atom, which is okay in this case. All your resonance structures a lot of times are going to have some type of deficiency a lot of times, so it's not like a big deal. It's mostly like looking at which ones have the fewest deficiencies when deciding which one's the most or which one's the best or most stable structure. So our next one's going to be something that we call an allylic move. So allylic move or allylic in general is just kind of a carbon like this that has a double bond right there and it can kind of flip. So when we're looking at like carbocation intermediates, those can be like allylic carbons and things like that, where things can switch and stuff like that. So in this case, our double bond is simply going to just move right on over to right there. And then that's going to give us CH2, CH, CH2. And then just going back and making sure that we include our positive charge on our left carbon. It's basically just flipping which one. So if we want to number the carbons, one, two, three, and the one on the left, carbon three, has the positive charge. Then on the right, um, carbon one has our positive charge in this case, or is our sextet atom. Both of these are actually pretty stable resonance structures. They actually are both equal in stability because there's nothing like really changing. It's just flipping, but they are two unique structures. So looking for allylic stuff is very important. Our last kind of common move that we have is forming a pi bond. So this happens a lot of times when you have lone pairs on an atom. You take a nitrogen or an oxygen, you can kind of bring it back to an atom that has a positive charge and form a double bond. So in this case, we're going to take this lone pair right here on this random atom, just using X as a placeholder, and we're going to bring it back there to help create a double bond between the carbon. So our resonance structure is going to look like this. We'll just assume that X has two other bonds coming off of it. It wants five. We'll just assume the X is a nitrogen in this case or something like that. Um, and the structure is going to be relatively stable overall. So that's pretty much it for the classic moves that we have um, for resonance structures and everything. But just making sure that you can recognize these and see these on like the exam, on the problem set, and stuff like that. So now we're going to move on and look at the problem set and do a little bit of practice with that. If you can hear the ringing, I apologize for that. Someone's messing with something in the building right now. But so with our first one, we are just looking at two carbon chain. We have a little ether group on the end and then a carbonyl carbon. So right off the bat, I recognize that carbonyl carbon, and that's where we're going to start. So for these, it's very easy to just break. I'll use red to break it like that and bring it around to the oxygen. And that's our first resonance. So on the problem set, I recommend kind of breaking it down like this, drawing your arrows, showing the movement of electrons so that one, you don't lose your electrons or create electrons. And then two, so that you end up with the same charges. That's another big thing. So with our structure over here, we're gonna have CH3, our carbon, then we'll have our O and CH3, just like that. And then our oxygen up here is going to have our negative charge, and our carbon right there is going to gain our positive charge. So that's one of our resonance structures in this case. And now we need to look at where we have electrons to move. So we've already messed around with electrons in the pi bond between the oxygen and the carbon. So moving them back would not be a new structure. It'd be the exact same as our original. So now we need to look where we have extra lone pairs to work with. And that's going to be on this next oxygen right here. So with one of these lone pairs, we're going to move it in between the carbon and that oxygen because the carbon has free space to take on more electrons or have an extra bond. So now we're going to do that, and it's going to give us CH3. See, this now is a double bond between the oxygen, and then our oxygen up here is still going to be negative, and we're going to get a positive charge here. So something to take note of, net charge, if you look at the charge for all of these, it's going to be zero here, negative and a positive, going to equal zero, and then once again a negative and a positive are going to equal zero, which is perfect. We want to make sure that we keep those charges the exact same across all of our structures. And so now we need to look at which one's more stable. And when doing that, you can go through those deficiencies. Over time, you kind of learn like you want to have the ones with the most bonds, the one with the least amount of charge. Like those are the big things to look for in your resonance structures in general. So if we're looking at the number of bonds, automatically, this one is not going to be it. It only has four bonds. This one has five bonds. This one also has five bonds. But then we look down at the charge. This one has charges. This one has no charge. Obviously, the charge is neutral across all of them, the net charge is. But the one on the left over here, which is our most stable resonance structure, has no partial charge or charges on the atoms that cancel out either. So moving on to our next one. So this one, we're going to start kind of with the same thing, looking at our carbonyl carbon. Add that lone pair right there. So the first step that we can do is break this carbonyl like that. It's going to give us CH3, C, another negative oxygen group up here, and then leave us with NH2, and then give us a positive down there. So we're looking at net charge. It's going to be 0, positive, negative equals 0. And then we're going to have another resonance structure. And another thing, resonance structures are shown by a double-ended arrow like this. It's not an equilibrium arrow because that's something that looks like this, like that, like that, and like that. And then a regular reaction arrow is just like that. Equilibrium or resonance is one that goes back and forth on both ends fully. It can fully switch in between both of them, and is different than any other type of arrow that we use. We also don't use like a single half arrow like that at all for resonance. It's always going to be our double-headed arrow like this. So what we can do now is with this lone pair on this nitrogen, since we have a positive charge on that carbon, we can take that lone pair and bring it in right there to help form another bond. So this resonance structure is going to be C, H3, C, double bonded in, H2. We're going to get a positive charge right there on that carbon or that nitrogen. And then our oxygen is going to have the negative charge, just like it did before. So if we're looking at our net charge, it's going to be positive, negative, going to equal 0 once again. And then we can kind of break it down and look at which one is more stable. So here we have 3 bonds, or it's a little bit more than that with the hydrogens and stuff, but just looking at the bonds in between the atoms, doing it that way. This one we have 4 bonds. When I'm counting them, I'm kind of looking at that one, this one, and those two. Here's that one, those, and then here we have 4 bonds. You can add in the hydrogen bonds, so it would be another 5 or so bonds between the carbon hydrogen bonds and the nitrogen hydrogen bonds. But the math is going to work out the same way. It would be 9, 8, and then 9 for the number of bonds. And then looking at the charges, so between the two that have 4, the one on the right has charges. This one, no charge. So it's going to be our more stable resonance structure. Now moving on to the last one. So this is one that you'll see on the exam, something like this. It's kind of a game. You're just constantly moving around the double bond. But I think like drawing your arrows here is super critical to making sure that you don't mess with the charge, don't add electrons, don't move the double bond too far. So we'll go over it now. So with this one, the double bond's going to kind of jump, filling where the carbocation is. So I'm going to try to draw this structure. Something like that. So these two double bonds right there stay the same for this one since there's nowhere for it to move to yet. But this double bond is going to shift up and our carbocation is going to come down right there to that end. And then we're going to repeat this process. So now this double bond down here is going to go there. So it's just moving to where a point of the double bond connects with that carbon so that it fills up its octet completely. So once we do that, we're going to just do this so it's easier. So if we're looking at the one right here, it's moved that double bond to be right here. And then it's moved the carbocation down here. And then we have one more possible move left. So let me duplicate this first. This double bond is going to go right there for our last one. And then erase this, erase that right there. And the carbon cation moves up to that position. And then at that position, there's no more double bonds for it to move or to jump to um, because they're all too far away at this point since we moved them all the way around. But then looking at the um, different structures for this one, so all of them have a positive charge. All of them have the same number of pi bonds, same number of bonds total. There's no difference in any of them besides like where the double bonds are, but that doesn't, in this case, doesn't actually affect the resonance stability. So all of them are going to be equal in stability. So make sure on the problem set you're circling if there's more than one that are equal in stability, circling all of them or both of them or all of them, depending on how many of them are the ones. So that's the resonance practice. And now we'll look at the last problem on the problem set here. So with this one, those outer, it's a little bit complicated in general, kind of figuring these out at first. On like the exam and stuff, they won't look exactly like this. It'll be a little bit more simpler. You won't have to be able to, you don't have to draw the products like this. Um, but he will ask questions over like the endo product versus the exo product and stuff like that. So making sure that you at least know kind of like what is what, and then which one's more favorable or the major product. And then in general, just understanding like how Dill's outer combines when you have one piece and then another piece. So with this, we're going to look at our two products in general. So here we have our endo product, and then here we have our exo product. So what makes each of these endo or exo? So we're looking at our large group, which is going to be this one, our CO2CH3. It's going to be our large group here. So endo means large group will be straight up or down. So it's going to look, if you want to think back to axial and equatorial in this case, our endo product is going to be in the axial position, and it's going to be called our endo product or endothermic. So endothermic versus exothermic product. And then on the right, we're looking at our exo product. And this is going to be where the large group will be slightly slanted or slightly angled up or down. So I wouldn't necessarily like always call them like the axial versus equatorial because they're not obviously you know the equatorial things are more stable and stuff like that. But in this case, it's going to be our kind of axial, we can say. If you want a way to remember the position better, and then this would be our equatorial group being the biggest on our extra product. So when we're looking at the major product, our our endo product is the major product. So just always remembering that which group is the endo group. It's very important. So just making sure that we circle that. So that's pretty much all for resonance practice and just kind of briefly going over those outer reactions and everything like that. Dr. Berg will cover this more in class. Just want to get this out there for the problem set um, and to get a head start on test three since it'll be coming up very soon. There will be a lot of reactions to learn, a lot of different things to learn for this test. So start your studying soon, come to office hours and ask questions. So I will see you all later.